Hello dear learners, in this lecture we will discuss about another problem which can be solved using branch and bound algorithm, and this problem is called traveling salesman or traveling salesperson problem. So first of all, let us look at the problem scenario. So we have given a set of cities and we are also given the distances between each pair of cities. It means we are given something like an adjacency matrix. Okay, so we are given the distance between each city and every other city, right? And the problem is to find the shortest possible tour that visits each city exactly once and returns to the starting point, right? So it means you have to start at some city, let us say city A, then you have to go through all the cities. Suppose in between there are n cities, and again you have to return back to city A, and this is the condition is that each city should be visited exactly once. Okay, so this is the condition which is similar to the Hamiltonian cycles. In the Hamiltonian cycles we visited each vertex once, exactly once, and we returned back to the starting point. But another condition here is that it should be the shortest possible tour. So the path through which you are going, it should be optimal, it should be shortest possible path, right? So this problem is known as the traveling salesperson problem. So here we have an example. In this example we are given cities 0, 1, 2 and 3. So there are 4 cities and we are also given the distances between each city, each pair of cities. Okay, so for example 0 to 1 the distance is 10, 0 to 2 the distance is 15, 0 to 3 the distance is 20 and so on. Okay, so if we want to start at 0 and we want that we should visit each city exactly once and return back to 0, then there might be several ways through which we can do it, right? We can start from 0. From 0 we can go to 2, then to 3, then to 1 and then again to 0. Okay, so here this is a Hamiltonian path, right? Hamiltonian cycle, because we are visiting each vertex exactly once. But there is another possibility in this graph. We can go from 0 to 3 to 2 to 1 to 0. Okay, so I think there might be some more possibilities, right? So these are not the only two choices. For example, we also have the possibility of going from 0 to 1 to 3 to 2 to 0, right? 0, 1, 3 to 0. Similarly, we also have another option of 0 to 3 to 1 to 2 to 0, right? So we have a number of choices, but the traveling salesperson problem is about finding the shortest possible tour. Okay, so here the shortest possible tour is 0 to 1 to 3 to 2 to 0. Okay, so this is the path or the cycle which is giving us the shortest possible tour. Its cost is minimum, right? So what is the cost? Cost is 0 to 1 it's 10, then 1 to 3 it's 25, then 3 to 2 it is 30, and then 3 to 2, 2 to 0 it is 15. So total it is 10 plus 25, 30 and 15, it is equal to 80, right? So this is the traveling salesperson problem. Okay, so now let us look at the branch and bound approach to this problem. So the branch and bound approach is similar to the examples which we did earlier. So earlier we have already done 0, 1 knapsack problem using branch and bound, and we have also done the job assignment problem using branch and bound. So the strategy which we use there is the same strategy we will use in this problem also. Okay, so for any current node means the node which we are going to explore currently, any E node. Okay, we compute a bound. Okay, so whenever we visit a node, we compute its bound. It can be an upper bound or a lower bound. Okay, so for minimization problems, we calculate a lower bound, and for maximization problems, we find an upper bound. Okay, so let us say bound. For every node which we are going to explore, we calculate or compute a bound on the best possible solution which we can get if we go down this node, right? So if the bound on the best possible solution, if its value, suppose its value is x, is worse than the current best, there might be some other nodes which have already been explored, not explored, I will say visited. Okay, so there might be some other live nodes. Okay, so they might have their own bounds. Suppose its bound is y, its bound is z. Okay, so if this bound is worse than the already best bound, suppose this is the already best bound, y is the already best bound. Okay, so if x is worse than y, then we will ignore this subtree, right? We will not explore this tree any further. Okay, so this will become a dead node, and we will explore the node which is having the best bound out of all the live nodes. So this was the strategy you might be able to recall, which we used in these problems also. Okay, so now there is a difference in different problems, means how do we found the bound, how do we calculate the bound. Okay, so in job assignment problem, we calculate the bound by picking up the minimum from each row. Okay, and in 0-1 knapsack problem, we calculate the bound using the greedy approach. Okay, so how do we calculate the bound in traveling salesman problem? The bound here is called cost. We will call it cost. Okay, so the cost through a node will include two costs. There will be two costs which will contribute to the overall cost of a node. So the first cost is the cost of reaching the node from the root. Okay, so this is the root node where we start the search, and this is the cost, first cost, the cost of reaching the node from the root. When we reach a node, we have already this cost. Okay, so we have already this cost computed. And the second cost is the cost of reaching an answer from the current node. Okay, so suppose this is cost 1 and this is cost 2 and this is our answer. Okay, so this cost is computed, we compute a bound on this cost. Okay, so whenever we want to explore this node, we will explore only if its bound is promising. Okay, if it is giving us the best bound. Okay, so this cost is computed when we compute the bound to decide whether to ignore this node's subtree or whether to explore this node's subtree. Okay, so the overall cost will be cost 1 plus cost 2, right? Okay, now let us see an example. Let us go through an example to solve a traveling salesperson problem. Okay, so the problem is this. This is the graph in which there are 4 nodes. It means 4 cities are there, and this is a directed graph, and we are given the cost of visiting different cities. Okay, So first of all, we will find the initial cost matrix. What is the initial cost matrix? It will be the adjacency matrix, simple. Okay, so this is the initial cost matrix. There are no self loops in this graph, so all the diagonal elements, they are 0, and other elements are filled according to this graph. For example, C to A, the distance is 11, C to A 11. Similarly, B to D, it is 18, B to D, it is 18. And similarly, we do not have any node from B to C, right? So this is B to C is infinity. In this manner, we populate this cost matrix, which is our initial cost matrix. Okay, so now we will go to the step 1 of this branch and bound algorithm, so which is reduce the initial cost matrix. So at every step there is a reduction. We reduce the matrix which is given to us. So how to reduce the matrix? So this is the graph. This was the matrix, initial cost matrix, right? Now reduction is done in 2 steps. Reduction by rows, we reduce by rows, and then we reduce by columns. Okay, so how to reduce by rows? In order to reduce a matrix by rows, from each row we pick the minimum. For example, here the minimum is 4, here the minimum is 5, here the minimum is 6, and here the minimum is 2. Okay, so we have picked the minimum values. Now how to reduce? We subtract this value from all the values in this row. So infinity minus 4 is infinity, 4 minus 4 is 0, 12 minus 4 is 8, 7 minus 4 is 3, right? Similarly, we will subtract 5 from all these values in second row. Okay, so it is 5 minus 5, 0, then infinity, infinity, 13. Similarly, here we will reduce by 6. So we will subtract 6 from all the values in this row. 11 minus 6, 5, then infinity, infinity, and 0. And the last row is reduced by 2. So it is 8, 0, 1, and infinity, right? So this is the resultant cost matrix after row reduction. Now we will reduce by columns. Okay, so it means from each column we will pick the minimum. In this column it is 0, in this column it is 0, in this column it is 1, in this column it is 0. So it means this column, this column, this column, they will be simply copied, but here we will reduce this column by 1. So it will be 7, infinity, infinity, 0. Okay, so after column reduction, this is the resultant matrix. So now we have reduced this matrix by rows, initial cost matrix by rows as well as columns. Okay, so now we are creating the node 1 in our tree, that is the root node. We are, through a reduction of initial cost matrix, we are going to create the root node of our search space. Okay, so this will be called node 1. Okay, so what is the cost of node 1? Cost of node 1 means we are finding a bound on the overall cost of the traveling salesperson problem on this graph, right? So that is this row sum, and this is actually not row sum, this is the values through which we reduced each row. Okay, so 4 plus 5 plus 6 plus 2, these are the row reduction values, and these are the column reduction values, 0, 0, 1, and 0. So the total is 18. So it means we have computed a bound or the cost of solving the traveling salesperson problem on this graph, right? And the bound is 18, right? So it means node 1's cost is 18. Okay, so here we are starting at A. So I forgot to mention in the beginning, so this is the a traveling salesperson problem on this graph, which is starting at A, and after starting at A, we will visit every vertex and then we will return back to A. Okay, so A is our node 1 here, and its cost is 18. So it means the overall cost of applying traveling salesperson problem on this graph by taking A as the initial node is 18. Okay, so from A we have picked A as the initial node. Then the second node which we can visit in this graph can be B, C or D, right? So let us call this node as node 2, this as node 3 and this as node 4. Okay, so now we will go to our step 2. Step 2 means we will explore now the level 2 of this. Suppose this is not level 2, this is suppose level 0. So now we will explore all the options at level 1. This option and this option, that is node 2, node 3 and node 4. So first let us pick node 2, that is vertex B. If we choose from A, we choose to go to B, then what will happen? What will be our cost? So node 2 means you are following the path A to B, right? Okay, so from the previous reduced matrix, in the previous step we reduced the initial cost matrix, right? So the reduced matrix of step 1, we will note M, A comma B. Okay, so what is in the matrix A comma B? A comma B is 0. Okay, so A comma B is 0. Then now we will create a new matrix in which we will set row A and column B to infinity and this cell MB comma A to infinity, right? So it means this will be the resultant matrix. So here we are setting row A to infinity and column B to infinity. So it means we are not able to go from A to any other node. Similarly, it means that we have the cost of going from A to B as infinity, and then B to B as infinity, C to B as infinity and D to B as infinity. Okay, so we have set this cost as infinity, and we are also setting B comma A this value to infinity, and rest of the values are same as the reduced matrix from step 1. Okay, so all other values are same except that we have set this row to infinity and we have set this row to infinity and we have set this value to infinity. Okay, so in this way we get this matrix. Okay, now we will reduce this matrix and find the cost of node 2, right? So first is row wise reduction. In this row there is all values are infinity, so we cannot reduce it. Here the minimum value is 13, 0 and 0. So when we reduce it, this is the resultant matrix, and now from this we will reduce it column wise. So in this column minimum is 5, here it is infinity, then 0 and 0. Okay, so when we reduce it we get this matrix. Okay, so we have reduced it by rows as well as by columns. Now we can find the cost of node 2, right? So what is the cost of node 2? Cost of node 2 includes two costs, as I told you in the one of the previous slides. It is the previous cost from the root, which is the root is A, the cost of getting from A to B, and then the second cost is cost of going from B to an answer. Okay, so how do we find this cost? Cost of 2 is cost of 1. This is our previous cost, right, which we get from step 1, plus the reduction cost. Reduction cost is 13 here and 5 here. Okay, plus we also need MA comma B, the cost of going from A to B. So we have noted it from the previous matrix, which is 0. So the overall cost is 36. So this is option 1. We have computed it. Now let us go to option 2, choosing to go to vertex C. In that case, the path will be A to C, and from the reduced matrix of step 1, we can note the value of A comma C, that is the cost of going from A to C, which is 7, right? And then we will set row A and column C, this time row A and column C to infinity, and we will also set MC comma A to infinity, right? So after setting these things to infinity, like we have set row A and column C, this should also have been infinity, right? And this is also infinity. Rest of the values are same. Okay, now we can reduce this matrix. So when we go for row wise reduction, then there is no reduction, right? Because all values are 0 or there is a dash. Okay, so after row reduction, the matrix is same. Similarly, after column reduction, the matrix is same. Now we can calculate the cost. Cost of node 3 is cost of 1, the reduction cost, and the cost of reaching from A to C. So cost of 1 is 18, the reduction cost is 0, and the cost of reaching from A to C is 7. So the overall cost is 25. Now we are getting a better cost. This is worse, going to be cost us 36. Picking this option gives us the cost 25, which is better, right? Now let us choose to go to vertex D, which is the third option which we have from the root node A. We have already explored node B, node C, and now we are going to explore this option, right? So it means the path is A to D and this node is numbered 4. Okay, and from the reduced matrix of step 1, we note the value MAD. So row A and column D, the value is 3. It means the cost of going from A to D is 3. And now we will set row A and column D to infinity in the matrix which we receive from step 1. We also set this value D comma A to infinity, and thus we obtain this cost matrix from the previous step. So this is also set to infinity. Okay, so now we will reduce this matrix row wise as well as column wise to find the cost of node 4. So when we reduce it row wise, the first row is infinity, second row the minimum value is 0, in the third row it is 5, in the fourth row it is 0. So when we reduce it row wise, then we receive this matrix, and now we reduce it column wise, but it is already reduced because the minimum values in first 3 rows are 0 and in the last row the value is infinity. Okay, so this is the matrix after reduction. Now we can compute the cost of node 4. This is the cost of node 1, this cost plus the reduction cost, that is 5, plus the cost of going from A to D, that is 3. So the total cost is 26, right? So we have executed the step 2. We have looked at all the nodes, all the options which were available to us at level 1 of the search tree, right? So we have found that cost of node 2 is 35 and the path is A to B. Cost of node 3 is 25 and the path is A to C. Cost of node 4 is 26 and the path is A to D. So now we will choose the node with the lowest cost. So it means we will choose node 3, that is C, and the path is A to C. And now we will explore this the subtree rooted at this node, in the next step, right? So this is how our search tree is looking like. Node 1's cost is 18, then we calculated the cost of node 3, node 2 and node 4 in step 2, right? Here we were at step 1 where we reduced the initial cost matrix, and now at step 2 the minimum cost is the cost of node 3. So we will explore this node. Okay, so from C we have already A in our path, we have C in our path. Now the only two options which are left are from C we can go to B or D. Okay, so now at step 3 we will explore these two options, the cost of going from C to B and the cost of going from C to D. Okay, so first let us choose going to vertex B. So the path will be A to C to B, and now from the reduced matrix, now we will use the reduced matrix of step 2, right? So here we will note the value of C comma B in the matrix, row C and column B, because the path is A to C to B, okay, and it is infinity in the reduced matrix of step 2. Now we will set row C and column B to infinity, and we will also set the value of cell B comma A to infinity. Okay, so because we are choosing the vertex B and the source or the starting point is node A. Okay, so after doing all these things we get this matrix. So here row C is infinity and column B is infinity, and also C comma B, row C and column B, yeah. So B comma A is infinity, and the rest of the values we have copied from the reduced matrix of step 2. Now we can reduce this matrix. So when we reduce this matrix row wise, we find that we can reduce this row, second row by 13 and the last row by 8. And so after row reduction, this is the matrix which we get, and now there is no need to reduce it by column because it is already reduced, so the result will be same. Now what is the total cost of node this is 5, right? Now cost of node 5 is cost of node 3, that is the node from which we reached this node. Okay, so that is node with label C. Okay, and then the reduction cost here is 13 plus 8, and also the value of MC comma B, which is infinity. So the overall cost is infinity. It means we cannot go from C to B. Okay, now let us explore the second option at step 3, which is choosing to go to vertex D. So now the path is A to C to D, and here we will note the value of the cell C comma D from the reduced matrix of step 2, and its value is 0. Now we will set row C and column D to infinity, and we will also set D comma A to infinity. After doing all these things, we get this matrix, not this row, this one. Row C, column D, they are infinity. Also D comma A is infinity, and the rest of the matrix we have got from the step 2, right? Now we reduce this matrix to get the cost of node 6, but you can note here that there is no value by which we can reduce this matrix. This matrix is already reduced, right? So no change, right? Now let us see what is the cost of this node 6. Cost of node 6 is cost of node 3 plus the reduction cost plus the value of MC comma D. So the cost of node 3 is 25, reduction cost here is 0, and the cost of MC comma D is also 0. So the overall cost is 25. Okay, so we have completed step 3. Now let us look at the scenario. So in step 3 we explored two nodes B and D, right? And the cost of B was found to be infinity and the cost of D was found to be 25. So it means we will leave this node and we will explore this node. Okay, so from this node what are the options left which we can explore? So we have got A, we have got C, then we have got D. So only node which is left is B. So it means from D we can explore B. So in the next step, that is step 4, we will explore vertex B from node 6, that is D. So we will start with the cost matrix which we received at step 3 for node 6, right? So this is the overall scenario. You can see here we started at node 1, its cost was 18. Then from node 1 we calculated the costs of node 2, 3 and 4, that is B, C and D, and out of these we found this one as promising. So we explored this node. So from this C node the options were B and D, that is node 5 and node 6. So we calculated the cost of these nodes. So the cost of D, that is node 6, found to be promising. So we explored this node and we got now we will explore this node, and it means from D we will explore this node 7, that is B, right? So now we are choosing to go to vertex B, that is node 7 in our tree. The path is A to C to D to B. Okay, so now we will take the reduced matrix of step 3. And from that we will note the value of D comma B, which is 0, and now we will set row D and column B to infinity, and we will also set B comma A, the cell B comma A, to infinity. And after doing all these things we got this. Okay, so everything is infinity here. Okay, so this is an already reduced matrix. Okay, so we do not need to reduce it. It means simply we can calculate the cost of node 7. So the cost of node 7 is the cost of node 6 plus the reduction cost plus the value which we noted from the previous matrix, that is the cost of going from D to B. So the overall cost is 25 plus 0 plus 0, it is equal to 25. So this is the overall cost of the traveling salesperson problem. So if you want to confirm yourself whether you have done all the calculations correct in this traveling salesperson problem, then you can look at the last matrix. The last matrix should contain all the values, all the cells set to infinity, like this, right? So it means we have done it right, and the optimal path is A to C to D to B to A, and the cost is 25. Right? So this is all about the traveling salesperson problem using branch and bound. Thank you.